So hi everyone, welcome. So this is designing resilient power grids, and basically what we're going to talk about the grid. And of course, in designing anything, the first thing you have to do is you have to understand all the parts that you're trying to put together, and understand the strengths, understand the weaknesses. So that's really what we're going to talk about. We're going to go over what the grid is, and we're going to talk about all the risks to the grid, and figure out ways that we can design more resilient power grids. So the first question I have for you is, what is the grid? And I know some of you have already know the answer. You want to give it to us? You forgot. Okay. What is it? Okay, so basically I have a switch, an electric switch here. So as you all know, when you turn on the light, or you turn on your television set, or you turn on your computer, something happens. There's energy or electricity that goes through to make things work. And what the grid is how we deliver electricity everywhere. It's basically all the wires, and how we make the electricity, and how we bring it to you. Is electricity important? I see nods. It's very important. Electricity is basically the backbone of our living, and has made our world what it is today. It's made our world a better place. As you travel around the world, places that have a higher usage of electricity are basically equates to quality of living. As you go, you go to places in Africa where they don't have electricity, their living is not as high quality, because they don't have clean water a lot of times, they don't have sanitation. We heat and cool our homes with electricity. We have access to lighting, so we can operate at all times of the day. We can go 24/7. Communication. Anybody here communicates with electricity? Exactly. Everything we have, our cell phones, our telephones, our computers, everything is powered by electricity. Entertainment. See nods? Yes? You all like to play games on your computers, right? Watch television shows, learning through the internet, and health support, of course, as we age, or some of us may not have the ability we may need cleaner environments, so we need to have air filters, or sometimes we may need to have life support. And especially for our elders, we might need devices in our homes to support their living or health. And of course, we know that cars are now being depend on electricity, especially like the Teslas and new cars that are being released over the many years. And so soon we're going to be using electricity a lot with our cars. So we're going to have a larger amount of electricity utilized with our cars. Can you imagine living without electricity? It's really impossible for us to do right now. So how does electricity get to us? The grid, yes, the grid. And so we call it the electricity or power grid. And the electricity power grid was developed many years ago when electricity became available. And normally what would happen is we would have these power plants that you usually don't see on a daily basis, because in the past these would be very dirty. They would have emissions from burning coal or oil, and so they located them in faraway places in the country, distributed throughout the United States. And then so we take that electricity, we use transformers to step it up, And one of the reasons we use transformers to step it up, and I'll talk about this a little bit later, is because as electricity travels through the wires, there's losses. So we find that the higher the voltage, the lower the loss. So keep in mind that we have losses during the generation, we have losses during the transformer or when we step it up, we have losses in the wires, and then we have losses in transformer, again, stepping it down in substations. And then we have our distribution, and then we have our usage or demand. So this is basically, and of course, this is a simplified version, right? Things get a little bit more complicated as we spread it out. The other thing I want you to think about, other than the losses, is that we also have assets. So we have the power plant, we have the wires, we have the infrastructure. So anytime something might happen, if this goes out, we have an interruption in power, right? So keep these things in mind as we move forward. The grid basics, as I said, we have a big network of high voltage power lines, overhead transmission lines that link the power generation to the power consumption. This is kind of like a picture of it throughout the United States. And on a national scale, this network is huge. So we have 450,000 miles of high voltage power lines and 160,000 miles of overhead transmission lines throughout the United States. That's a huge amount of lines. Do you guys ever see these types of lines anywhere? You see them when you travel, right? So again, the network consists of generation, where we supply the energy, transmission and distribution, which is a way that we get the energy from the supplier to the consumer, and we call that demand. In the past, we haven't really had ways to store energy, to store electricity. So, because we don't have that storing capability, we have to produce and deliver power or energy or electricity in real time. So what that does is it creates some sort of a challenge for the operators and the people who are managing the grid, because what they have to do is they have to make sure that anytime you turn on that switch, that energy is available to you. So they don't have the freedom of just saying, just turn on the switch and then we'll turn on the generator and we'll bring that energy to you. They have to constantly manage, and they have to constantly keep generators and supply of electricity constantly available for your need. So that makes the demand or the shifts of power, demand, and supply very challenging. The other thing I want you to also think about is, remember what I said to you about power losses, right? So when we actually look at it, about 65% of the energy used to generate, to convert, to transmit electricity gets lost in the process. So we take 100% of coal, 100% of oil, we burn it. As we burn it, we only convert about 35% of it into electrical energy. Then we take it, we transmit it, and it comes to you. And so we lose 65% of that energy, total energy. So generally speaking, we need 3 watts of raw energy for every 1 watt of demand. This is very important for us to understand, because a lot of times the best way for us to reduce our dependence is by having a more efficient use of energy. So therefore, the watts that we demand, or the watts that we need, are much fewer than maybe the ones we're using. So we would need less energy, raw energy, to supply us this demand. Make sense? All right, so looking at the electricity generation, or the supply of energy, of electricity, since the Industrial Revolution, the process is basically pretty much the same. So what we do is we generate steam by burning fuel. Some of it becomes electricity, most of it becomes heat. And then we use that steam to rotate large turbines. And the turbines have electromagnets, they're large electromagnets. And by using the electromagnetic principles, we're able to convert that motion into electrons that move through the wires, that generate electric current, and basically provide us the electricity that we need to do the work. And normally, coal was the first fuel that we used. Oil was the second one. Oil is a little bit cleaner than coal. Then we got to natural gas, which is being utilized now more and more. And that's actually one of the reasons why the use of coal is going down, because natural gas is much cheaper, much cleaner. And the other thing with natural gas is we can have smaller generators. And then we also have nuclear energy, but nuclear energy has some problems with the hazard. It's a hazardous material, so it's very hard to get rid of. And I showed here pictures of nuclear energy power plants. This would be a coal energy power plant. And then we also have other ways of moving turbines. So as you can imagine, moving a turbine, we need some sort of way to move it. And so we use hydroelectric dams where gravity is doing all the work. These are clean ways of generating electricity. But the only problem that we have is the amount of water. If we don't have enough water to keep those hydroelectric dams moving, then we have a problem, because the life of the hydro dam might be reduced. Then we have wind. Wind is a new form of turbine movement or generation, but it has become very popular because of the cost. We can actually generate electricity at about 2 cents per kilowatt hour by using wind. And that's the cheapest form of energy right now. The cheapest form of electricity is wind. Then is solar, and then is natural gas. And of course we have waves. Wave technology is basically similar to the hydroelectric, but we're putting turbines inside the ocean, and we're taking advantage of the currents in the ocean. And we also have new forms of electricity generation, one being the solar photovoltaic panels. Like, as I said before, solar the prices have come down greatly, and you can actually do solar at around 3.5, 4 cents per kilowatt hour. The only problem with solar is that a lot of times, we might have it's intermittent because of clouds, because we don't have it during the evening hours. And without the ability to store that energy, it's not as dependable as turning on the switch and burning oil or coal. And then we also have fuel cells, which are electrochemical processes that produce electricity. The optimum for a fuel cell is to use hydrogen and have no type of exhaust or emissions. Most of the time, right now, they're using natural gas. electricity transmission. As we talked about, electricity transmission is an important part of the electrical grid. Think about the 450,000 miles of wiring that goes from the west to the east and all around the country. So, and as I talked about, we go through large distances, and we basically transform the voltage to typically about 110 to about 765,000 volts as a way to reduce the amount of energy lost in the power lines. Transmission lines are usually overhead. You've seen these things on your travels, right? Everybody has seen these types of transmission lines and towers. The reason they do this is because it's cheaper than putting them in the ground. You don't have to dig. It's less intrusive, and in the event of a problem, they're easier to fix. You don't have to go in the ground and dig and all that. Transmission lines are interconnected throughout the United States. And as you can see here, there's multiple connection points to every consumer. And the reason they do that is to offer the operator flexibility in the event there's an interruption. So let's say there's a break in this line right here. Well, you can supply the power from another source. So it's a quick way for the operators to reroute the energy, and in the event you have loss, you can get that energy back, that electricity back, so you can continue your living. Because as we said before, we can't live without electricity, so we want that electricity as soon as possible in the event of an event. Electricity distribution. So electricity distribution is basically after they distribute the electricity throughout the country, it gets near you. That's the place where the local delivery happens. And this is how we deliver the electricity to your community. The electricity steps down down to about 50,000 volts, and later on, as it gets closer to your home, it steps down even further, and until it gets to your home around at 240 volts. And that's where the electricity gets into your house. The electrical distributor or the operator of that neighborhood or the state or the region is usually the people who are operating the distribution network. They own, they operate, and they make sure everything is reliable. They make sure they make sure that electricity is constantly, reliably, and safely delivered to your home. And part of their service includes the meter reading, maintaining those lines and making sure everything is working properly, and responding to outages. So who's your local distributor in your neighborhood? Yeah?
Pico.
Pico? There you go. In the event something happens, Pico, you see the Pico trucks coming out and trying to fix it, right? Anybody else? Anybody from New Jersey? Yeah.
Delmarva.
What is it?
Delmarva.
Oh, Delmarva. Is that Delaware?
It's all.
Delaware, Maryland. Maryland. Oh, great. Great. So finally, the electricity reaches your home and you use it. So as it enters your home, there's a meter. It measures your consumption. The utility company will take that information and charge you. And here we're also talking about how in the past, the meter was an analog meter. Does anybody have an analog meter at your house? Analog meters basically look like a little wheel. And if you go out and you look at the meter, you can actually see the wheel turn. Anybody familiar with that? Yeah. You have one?
Yeah.
All right. So, as a way to improve the resilience, improve the dependability and the response of the grid, I don't know if you've ever heard of it, but there's the idea of a smart grid. So a smart grid means that you actually have information available to you so you can make decisions about the supply and demand of the grid. And one of the effects of that is that what utility companies are now doing is they're starting to install smart meters. Smart meters are digital meters. They measure the electricity that you're using, your usage, and they report it directly to the utility. So this way the utility can make a more accurate reading and they can respond to anything that happens. So in the event your meter goes down, they know there's a problem, they know they have to fix it, maybe they can send someone out there and see what's going on. If there's more meters in your neighborhood, maybe there's a problem with the transformer. So they have a better way of assessing information and responding to it. Challenges to the electricity grid today. So the biggest challenge is that we have an aging infrastructure. You know, many of these lines, many of these assets, the generators, and all that, they have been installed over the years. Many of them are very old, and many of them need to be replaced. So there's a huge cost to that. If you look at here, the replacement value of the grid is estimated at $4.8 trillion. And of course, imagine how much work needs to be done to replace or improve. The other problem is that you have an increased need for electricity. So we have more and more reasons as we use electricity to provide us information, as we depend more on in communicating with each other, as we do more of our work in the cloud. The cloud is not some cloud out there that doesn't exist. It actually consists of large data centers. You've heard of data centers, right? So, a place where you can store information, a place where you go and access websites and information like that. So all that takes additional amount of need or higher demand. So today about 70% of the power grids, lines, and transformers are over 25 years old. And as our needs for electricity increase, we have higher stresses on the actual grid system. Other challenges to the grid, we have vulnerability to exposed infrastructure. I'm sure all of you, especially the past few years, we've had some ice storms. Have you guys seen where the electrical wires get loaded with ice and they sag real low and they could break? That becomes a big problem. And another big problem is finding ways to integrate greater renewable energy generation. Because a lot of times these things are intermittent, or the place where we can get a lot of wind is maybe in the Midwest. So somehow we have to integrate and bring that energy back into the places where it's being utilized. So a lot of the population lives on the shores or on the east and west coast, but the energy is in the middle of the country, so somehow we have to add capacity to bring it to those locations. Other challenges have to do with storms and severe weather. We all know about Sandy. Anybody lose power during Sandy? For many days, right? So what happens during big storms? We have flooding. We have things flying around, knock down poles. They knock down the transmission towers. And of course we have fallen trees that fall down and they cut the lines. Another thing that's coming up, it's a developing concern, is cybersecurity attacks. As you remember when I talked about smart meters, we're trying to create a smart grid. Smart grid means that you have communication between devices, supplies, generators. So as that happens, as you increase the amount of communication between all the assets, you have the possibility that someone could hack into and then could mess up your distribution network. Any questions? All right, so knowing all this stuff, how do we make the electricity grid more resilient? So there's 4 different ways, and these 4 different ways match the 4 ways that the grid operates, right? They match the generation, the transmission, the distribution, and the demand. So we can smarten the grid. By smartening the grid, we have the ability to bypass, to use resources more efficient, and improve its operation. We can harden the grid. Hardening the grid means that we take those assets and we support them, or we do different things to improve the infrastructure. We can do things by making our generation more resilient, and here we're talking about distributed generation. So instead of relying on a factory out in the Midwest that has many points of failure, maybe we can generate electricity more locally where we use it, where we need it, and then eliminate all those points of failure. Or maybe we can rely on that in times of an emergency. Oops. And of course, building resilience on the demand, which would be where we use the energy. So we can become self-resilient. Maybe, I don't know if you've ever seen, but lately, a lot of people are installing solar on their homes. A lot of people are installing backup generators. So that makes you less dependent on any problems that might happen with the overall system. So the first thing is smartening the grid. What we're doing with smartening the grid is we are incorporating advanced meter. So that would be the smart meter, right? So the smart meter stands there, collects information, sends the information to the utility office. They have a better idea of what's going on in the neighborhood. Then we have distributed automation. So distributed automation deployment would mean that, you know, we can shut off some of the causes of the problem, or we can manage the demand, or if there's a disturbance in the grid, we can isolate it. And this way, by smartening the grid, we're able to incorporate new technologies, create a kind of like an artificial environment where we can actually look at all the different problems and all the different needs, and we can manage them better so that we can improve the resiliency of the system. Hardening the grid. So in hardening the grid, we can look at the assets that are at risk, and we can raise seawalls around the key assets if they're near an area where there's a lot of water or the potential of flooding. We can restore natural coastal protections. Another thing we can do is we can relocate key assets. So here's a picture where this is a substation that had consistent flooding. So what they did was they took the old equipment, created a new substation which is at a higher ground, and this way they were able to mitigate the risk. Undergrounding power lines. This is definitely, I don't know if you've seen some neighborhoods that don't have any overhead power lines. Those are usually underground. Those neighborhoods usually don't have problems with fallen trees. They don't have problems with things flying around and knocking down poles. They don't have problems with poles becoming old and leaning over and cracking and falling. Now, the problem here is that this would be a very expensive proposition because you would have to dig miles and miles of ditches in order to take all those 450,000 miles of wiring and put them on the ground. Expanding tree trimming program. So like your local utility will identify all the trees that need trimming, and they would basically, this is kind of like an exaggerated example, but basically this is what they would have to do. They would have to look at the tree, determine which part of it is risky, and they would go and cut it out. And I think you do see, I don't know if you noticed, but in your neighborhoods, you probably see the utility coming around in the springtime and cutting down trees and clearing out risky branches. And another thing we can also do is we can have improved transmission line materials, such as high temperature, low side conductors. Distributing generation on the supply side. So, distributed generation, again, means that we're not generating far away from us, but we're actually bringing the generation closer. And we usually do that with solar. A lot of people are putting solar on their homes. We could have wind generators. One of the things that doesn't mention here, but I don't know if you've heard of microgrids. So what's interesting is many institutions, probably this building, data centers. I know Comcast or communications providers, clinics, hospitals, a lot of big buildings, what they have is they usually have a backup generator, or they have a way of continuing operation through maybe some sort of a UPS or an energy storage system. I don't know, do you guys have UPSs on your computers? You do? Okay. And even personal computers. Personal computers, believe it or not, because they have a battery, that's your UPS. So you disconnect from the grid, your battery is stored, you can use it for the next 5 to 10 hours. So a lot of users, a lot of buildings, maybe even schools, I don't know if all schools have them, but there are some schools, I know universities have them, they usually have a way of protecting the data. And the way that they protect the data, they have a UPS that's on standby. So if something happens, the UPS kicks in, it maintains power for half an hour to an hour, and then you have a generator that kicks in and keeps things going until the grid comes back. Well, we can actually take control of those assets, and we can actually use those assets to provide ourselves with an isolated way of providing energy for the needs that we have. So this is one way, okay? So you can see it here, utility-owned combustion turbines for peak power. That's one way that we can locally distribute. We can have generation at the local level and distributed generation. We can have customer-owned diesel generation. That's what I was talking about with hospitals and universities, where they have these types of generators available. Why not use them most of the time and not only during an emergency? It's possible. And then we have customer-owned grid-connected CHP systems. This is a combined heat and power system. The difference between the diesel generator and the CHP is that the CHP is basically a generator, but it also has the ability to capture the heat. A lot of times you may have heard the word cogeneration. So, I don't know if you recall, but when I first started, I was telling you that 65% of the energy gets lost. Much of it gets lost during the generation of electricity. Well, if we can capture the heat from the engine when the electricity is being produced, then we can increase the efficiency of that engine from 35–36% up to about 70–75%. And that's the idea of the CHP systems. So what they do is they capture that heat, and then they can take that heat and use it to heat the building. Or what we could do is we could take that heat, create a heat absorption cooling. We can actually turn the heat into cooling power, which is pretty amazing. And of course, microgrids. Microgrid is basically what these customers' diesel generation systems, if you have a way of controlling your sources of energy and your uses of energy, and you have a smart system that can balance those things, that's what we call a microgrid, which includes the CHP, renewable power, and other elements. So what microgrid does, we have a control system. It looks at the available sources of energy. It looks at what are our needs, what's the demand, what are the loads that we're using, and then it balances it automatically through a digital system. So this is one way that we can create resiliency in the grid on the generation side. And building resiliency on the demand side, well, again, it goes back to the ability to manage things, right? So by having battery storage, we can have locally the amount of electricity that we need. By using addressable thermostats or other types of appliances, and I know you've seen them, right? On Amazon, you go on Amazon, you do a search for programmable thermostats, you can see a list of controllers for your lights that you can control from your telephone, from your cell phone. And there's all kinds of appliances that we can now control from our phones. That goes back to what I was saying about microgrid, right? Once we have battery storage, once we have the ability to manage all the uses of energy, and we can program them, or we can offset them, or we can do different things with them. In essence, what we're doing is we're creating a microgrid for the ability to manage the sources and uses of energy. Then other ways that we can do it is by needing less energy, right? We have energy efficient buildings. So what does that mean? It means by using thermal insulation, by making our buildings, by having better windows, by having fewer leaks of energy. What that means is we need less energy to power our building. The less energy we need, the less dependent we are on the grid. So advances in energy storage technologies allows the electricity to be stored, and it allows us to manage our electricity better. Hold on. All right. So this is where I call this critical thinking, because basically I went over explaining what the grid is, explaining or looking at the risks of the grid, and looking for ways that the industry, approaches that the industry is taking to improve resilience. But here's your input, or your opportunity to think about these things and think of ways that you can contribute to this. Can you think of ways to build resilience into the grid? Any ideas? What would you do to make the grid more resilient? Thinking about the generation, the transmission, the distribution, and the usage. Anybody? Yes?
Putting the transmission lines underground or in places that trees can't fall on them.
Put them where?
Put them underground or where trees cannot fall on them.
Okay. So it's part of what we were talking about, right? Now would that be an easy task or a difficult task?
Difficult.
Difficult. Would it cost a lot of money or not at all?
A lot.
Yeah, that's good. Good thinking. Yeah? we had somebody here? Yes.
Decrease the distance between your production and consumption of the electricity.
Okay, great, great. So that's along the lines of distributed generation, right? That's bringing it closer. Very good. So this way you get rid of that long distance and you reduce the risks. You had something here? No? You were just holding your glasses. All right. So here's another critical question. Do we need the grid? So the grid developed during a time when we didn't have a lot of technology, right? We had no storage, and it did make our life better. And in the near future, we need the grid, right? Because it's an infrastructure technology that we depend upon, and it's in place. So it's kind of hard to go from one kind of infrastructure to another. I give an example of the car. Electric cars are more efficient, they last longer, they have fewer parts, they only have 10% of the parts. Well, actually they have like 12 parts, where a regular car that we drive has thousands of parts. So it's a much simpler technology, it lasts longer. We could drive an electric car for 500,000 miles and it will still keep going because it has very few parts. And it's a more efficient way of walking around, but the problem is that we have an infrastructure for gas. So anytime we want to go from infrastructure of gas, we want to go to a hydrogen-based car, we want to go to an electric car, what we have to do is we have to develop the infrastructure. And when the infrastructure exists, it's very hard to get rid of it, for lack of better words. Because we have to develop a new infrastructure, right? So there's a cost associated, there's energy, effort, all that. So in reality, with the technology that we have right now, we probably don't need the grid, but we can't live without the grid, so we're going to keep it. What would the future look like? Anybody? What do you think the future looks like? Yes?
Less power outages.
Less power outages? What else? Anybody else? Yes?
More efficient ways to use electricity.
Yeah, more efficient ways to use electricity, which would lead to less power outages. What else? Anybody else? Think. Yeah.
Less watts being produced to produce one watt.
Less?
Less watts being produced to use one watt.
Okay. More efficient, right? Yeah, that's good. Yeah.
A wireless grid.
Wireless grid. Okay, so that would be being able to transmit electricity wirelessly. That would be great. It's possible. Tesla did it years ago. So here's what I think the future looks like. I think the future looks very bright because we have the technology to produce electricity in many different ways. We have the technology to store electricity. And we also have the technology, as we're developing it, to control the sources and uses of energy or electricity. So I believe that this is what's going to happen in the future. What's going to happen is you're going to have everybody will have their own ability to generate, store, and manage electricity in their own homes. And of course, industry as well. But this probably is not going to happen immediately because there are many interests. The utilities do not want to lose that market. But I think long term, this is what's going to happen. So, any questions? Yes.
In your setup there, you showed solar. And what other possible generation systems do you think for that future?
So one way that I think is good is, of course, you have It all depends on the storage of energy, right? Because what we do is we can always generate solar electricity through solar means. Question is, how do we store it? So one way of storing it is batteries. Another way of storing it is we can create hydrogen, and we can store it, so we can transform the material into a usable gas that then can be utilized in a fuel cell too. But you know, it all depends. Again, it all depends on the economies and it depends on the technology that will be developed in the future. But I think that's where it's going because it's the most efficient way. You know, imagine if you can. A lot of people talk about solar that it doesn't have good efficiency, but in reality, efficiency in solar translates to land space. If you don't use a lot of electricity in your home, if your demand is low, you don't need a lot of space for the solar that you're going to be using. And the other thing with solar, the great thing with solar is that you can produce it locally. You don't need to have solar panels in Nevada in order for you to get the electricity in New Jersey or Pennsylvania. You can put those solar panels where you live, and you can generate that electricity. I have solar panels in my home. It's great. So being able to generate that electricity where you use it, and then being able to store it, and you know, of course, being able to manage those sources and uses of energy is really part of the key. So we have the artificial intelligence, we have the controls. You can see those controls permeated throughout as you're shopping around for programmable type of devices, right? So you're able to manage your heat, you're able to manage your lighting, you're able to manage everything. So that's really where it's going, I think. Yeah.
I recently saw a program that mentioned Idea House for a net zero home. How feasible is going to a net zero home right now?
Right. So net zero means that the amount of energy you use is the amount of energy you generate. So I would say my home is net zero. Now, because of the regulatory environment, I can't use my solar energy unless I'm off the grid. So in order for me to use my solar energy, I would have to have batteries, or I would have to have exactly what I was talking about. So the way that my system is, I actually have to generate electricity, feed it into the grid, and then the grid gives me back electricity, right? So because of the regulatory system, I can't do it. And if you see my house, the first thing I did when I wanted to do solar in my home, first thing I did was I created a lot of efficiency. So I reduced my cooling needs, because that's like the big part of your home energy needs, is basically cooling and heating. So if you can reduce that by adding insulation and improving the efficiency of the cooling inside your home, then you need less energy. What that translates on is that you need fewer panels on your roof to generate the electricity you need. So if you look at my roof, I don't have a very big house, but you look at my roof, it's basically 1/3 of 1/2 of my roof is solar. And that takes care of my whole house. Now I remember 20 years ago, I used to go, there were some guys that were doing research in New Jersey, and they actually had standalone homes that used no outside sources of energy. And that was 20 years ago. Yep.
In your opinion, what do you think is the most efficient way of like transmission?
Most efficient? Well, the most efficient way of transmission is actually DC. Even though we use AC, but actually DC that's what they're trying to do. They're trying to do high voltage DC systems. They're more efficient than the AC. The other thing I also want to mention is, if you think about the cost of a grid. So I visited Nigeria. So in Nigeria, one of the things you notice is they have no wires, but they have cell phones. So they bypassed the wire when it came to communication, right? And why did they bypass it? It wasn't done intentionally. It was done because they never installed the telecommunication system. But when cell phone came out, they bought cell phones and they have cell towers, and so they bypassed them. Now, when it comes to electricity, right? The majority of the world doesn't have an electrical system. The cost of installing an electrical system is going to be enormous around the world. People around the world want a higher quality living. The way you get higher quality living is by energy, right? Electricity. So in order for all these people to achieve a higher quality of living, the only means and the only way they can do it, the cheapest way and the fastest way, is if they had stand-alone distributed generation systems. So the only way they could have it is if they had their homes battery and a power or electricity generator.
Thank you so much for speaking for us today, and we appreciate all of you coming out and being part of the fair. We have a little bit of time left, so if you haven't visited all of our exhibitors, please be sure to do so, and make sure you get your bingo card filled out and drop it off at the front desk to be registered for a prize. Thank you.
Thank you. Enjoy the competition.